So like I said, we're going to do exam 2 review. Then we're going to cover chapter 5. Exam 2 is all multiple choice. So I've got some questions that I pulled from the exam 2 review that I posted. And after this session, the answer key should be available to you on Blackboard. So the same folder that has the exam 2 review in it should also have the answer key. We're going to go ahead and get started with this first question. I'm going to give you 2 minutes to jot it down in your notebook, work it out, and then I'll check back in, see how everybody's doing, and see if we got an answer. And that's how we're going to work it for all of these exam review questions. If you have questions during that wait period, feel free to put it in the chat and I'll address it. Until then, try this question and I'll check in 2 minutes. You can go ahead and put your answer in the chat. So it looks like those of you that have put your answers in, that we are converging on B. So let's walk through it, just in case there are some folks who were like, wait, what? This 60 here, cobalt-60. What does the 60 mean? It's not the atomic number, but it is a specific type of number. Yeah, it's the mass number. And that means that it's the sum of all the protons plus all the neutrons. Where can you find the number of protons in cobalt? You look at the periodic table. That's where the atomic number comes in. So when you look that up, you should find that on the periodic table, the atomic number is 27. So your mass number is 60. The number of protons is 27. And the question is asking you about the number of neutrons. So if you subtract 27 from 60, you should get 33. So those of you who participated got it right. And hopefully those of you who are just joining us or who didn't share your answer, hopefully you feel comfortable with this. We ready to move on to the next question? Resounding yes. All right. So for this one, we're looking at the following properties of gasoline. And what you need to do is tell me which of the following properties is a chemical property. I'll give you a minute to do it. And you can put your answer in the chat. Okay, so it's 2:15. And it looks like everyone that has chimed in with an answer has said A. Now I realized that I wasn't recording for the last question that we did. on the physical versus chemical properties. So it may be kind of a little bit of a jump to go from this question to the next one if you're watching the video. The notes will still have it, but the video will not have that question. So that's one of those things you just had to be there to get it. Okay, so now we're dealing with element X, and it's got two natural isotopes. I like to make my table. The first isotope is X63. In the atomic mass, we can fill in. The second isotope is X65, and we're also given that atomic mass. And finally, we're given the percent abundance of X63. How do we write that percentage as a decimal? You divide it by 100, and you get 0.6917. So when you divide by 100, that moves your decimal point over to the left by 2 spots. Only 2 places. So let me draw that in a different color so you can see it a little bit better. When you're dividing by 100, you're moving 2 decimal places to the left. Notice that we don't have a percent abundance for X65. How do we figure that out? Yeah, you have to know that the total percentage is 100%. That's how percents work. So if you subtract the percent abundance of X63 from 100%, you get 30.83%. Then you can write that as a decimal as well. Now we're ready to set up our equation. Yeah. So to recap, we filled in all the information that we knew. We were not directly given the percent abundance of X65. However, because we know that the percent abundance has to equal 100%, we can subtract the percent abundance of X63 from 100, and that will give us the remaining percentage for X65. Is that clear? Okay. So now we set up our equation. So this is what you should be doing in your calculator. And each of these pieces tells you the contribution to the atomic mass from each of the isotopes. You can know just by looking at the percent abundance that the atomic mass that's going to be reported in the periodic table is going to be closer to 62.94 because most of element X is in the X63 isotope form. When you put all this into your calculator, you should get 63.55. There may be another decimal or two after that. So the correct answer is A. One way that you can rule out two answers without even touching your calculator is by knowing that the atomic mass has to be somewhere between the mass of the one isotope and the mass of the other. So it can't be any bigger than 64.928 AMU. So you can automatically rule out D and E. So how does this problem feel? There's definitely going to be one of these on the exam. So just be ready. Now we're moving on to electron configurations. I'm not going to make you write them out in Blackboard because that would be tedious and having to go through and do the superscript for every little thing, and no. So it's multiple choice. Here's a sample question. Which atom has an electron configuration of, and then you've got this long configuration here. So using your understanding of the periodic table, tell me which one it is. So everyone who's chimed in so far has said B. I'll give another few seconds for those who are still trying to figure it out. But I'm just going to mark down B as what everybody's saying. So it looks like we're all going with B here. And I agree. The way that you can figure this out is by looking at your periodic table, and if you have your cheat sheet where all the S's and the P's and the D's and things are marked for each row on the periodic table, then you can just find the place where the 4D energy level, or energy sublevel, is full. And so the location of that is going to be in row 5 in the D block. The only thing that fits that is cadmium. Now, as practice, what I want you to do is write the electron configuration for tin. Its symbol is SN. I don't want you to spend 20 minutes trying to find it, like, where's tin? It's SN. So write the electron configuration for tin. Don't worry about putting it into the chat. I will just write it up on the screen and you can check your work. So I will give you 2 minutes and then I'll check back in. I'm going to start writing the electron configuration up. Check it against your work. As always, you start with the 1s. You fill that with 2 electrons. Then you move to the second row, still in the s block, and you fill the s orbital. Then you go across to the p block, still in energy level 2. We're going to fill that up. Now that we've filled all the spaces in energy level 2, we're going to move on to the third energy level and fill the 3s. Walk across to the p block and fill that. We're still not at 10 yet. 10 is in the 5th row. We're only finishing up the 3rd. So that means we've got to fill in the 4s. After we fill in the 4s, we go back and fill in the 3d. Then we continue on to the 4p and fill that. The next row is the 5th energy level. So we're in the town of 10. Just not quite there yet. We're going to fill the s. Then we're going to fill the 4d. And now we're in 10's neighborhood. So you count, and you'll see that you've got 2 electrons in the p block. So that's the full configuration for 10. Are there questions about that? I don't think that we're going to have time to do another electron configuration, just because we have to also finish the exam review and cover chapter 5. So if you need more help with that, office hours have been set to Wednesdays from 2 to 4. If that does not fit with your schedule, you can certainly send me a message through course messages on Blackboard and set up an individual time. So we do not have more time to do that today. If we have time at the end, absolutely just remind me, because I could forget. But we likely won't, okay? And also that video that I posted on electron configurations, it's a really good video. So if you haven't had a chance to watch it and you're struggling, watch that video because it may help you. It's more visual, and I'm a visual learner, so it may help. Okay. So now we're going to go on to do 2 questions. This first question, I'm going to help you out a little bit because it seems like it's coming out of left field. It was covered in the YouTube lecture, but we didn't address it specifically in our live lecture. So you have limestone decomposing by heat to create 8.51 grams of calcium oxide and 1.6 grams of carbon dioxide gas. And the question is asking, what was the mass of the limestone? I talked in the video briefly about the law of conservation of mass. When you're doing a chemical reaction, all the ingredients that you're pulling together, like if you're making, a cake, you'd bring the flour and the sugar, maybe you'd use a little milk, vanilla. You're gathering all those ingredients. Those ingredients are the reactants. The mass of all those ingredients is going to equal the mass of your products. So if you used a certain amount of flour and sugar and everything else and you added all that stuff up, the product that you get at the end, the cake, should equal approximately the mass of the stuff that you started with. So the key to this problem is identifying the reactants and the products, and then you can figure out the mass of the limestone. So with that hint, go ahead and try this first question, and if you get that or you're stumped, move on to the second one. So I will give you 3 minutes, and then I'll check back in. All right. So let's tackle this first one because I know it may still be a little bit of a question mark. But once you see it, you're going to be like, oh, really? Limestone decomposes by heat to give these two products, calcium oxide and carbon dioxide gas. So we're going to write limestone over here for our reactants. I'm going to write the chemical formulas for these as shorthand. No, you don't know how to do this yet, but you will by the end of chapter 6. So that's our carbon dioxide gas and our calcium oxide. In terms of the masses, we made 8.51 grams of the calcium oxide and 1.60 grams of the carbon dioxide gas. We don't know how many grams of limestone we started with. That's what the question is asking. If we add together the masses of the two products, we'd get 10.11 grams. So that's the mass of all the products. Since there's only one reactant, the mass of the limestone has to equal the mass of both of those products. So the mass of the limestone is 10.11 grams. Does that make sense? You will have, yep, that's it. I told you, once I showed you, you were like, so really? So we just gonna add? That's it. The only other variation that you might see is, let's say that I gave you a mass of limestone. Yeah, I'm going to kind of cover that. Let's say I gave you the mass of the limestone and the mass of the calcium oxide. Then I could ask you, what would the mass of the carbon dioxide be? In that case, you would take the mass of the reactants, subtract what you know about the products, and the rest would be carbon dioxide. So to put the numbers to it, let's say I told you that you had 10.11 grams of limestone and 8.51 grams of calcium oxide, and you needed to figure out how much carbon dioxide. You would subtract. Those are literally the only two real variations that you can have. So if this makes sense to you, you'll be fine for that question. We ready to go over the second question on here? So how many carbon atoms do we have? I think I saw one answer up there. Do you have any others? Yeah, so you should get 57. And for anyone who didn't get it or you don't understand, I'll show you how. It's just a counting game. All the places where you see a C, that's carbon. I'm going to kind of exaggerate these parentheses here. So to figure out how many carbon atoms, well, we've got 3, because that's what that subscript says. Plus, we've got some carbons in parentheses. We have 17 plus the 1. Just like in math, when you see a number outside the parentheses, no, you only distribute the 3. So that it would be 3 plus 3 times 18. And that should give you 57. So you total up the number of carbons inside of the parentheses and multiply that by 3. Then you have to be sure to add on the extra 3 carbons that are on the outside of the parentheses. So several of you got the 57. Has this helped make it a little bit clearer for those of you who didn't get it? So just a public announcement. The class is for everybody. So if you're just logging in and sitting back and chilling, or if you kind of feel afraid to say something because you don't understand, you're losing out. You're really losing out. So don't let the class just steamroll ahead and you're stuck on slide number 2. There's no reason for that. And if you still don't feel comfortable, you can send me a private message, or you can send me a course message through Blackboard. So don't just sit and stew. Reach out. So that's it for the exam review portion. Again, exam 2 is going to be available tomorrow. And it's going to stay available until the end of Friday. So 11:59 p.m. Eastern Time, it will disappear. It's all multiple choice. You do not need to upload your work this time. I've started grading your exam 1s. It just takes me a little bit longer because for partial credit, I also have to look at your work. So give me a little bit of grace, but I'm working on that. So you should have those grades. And then as you complete your exam 2, you will also see what your score is for that. You will not see your score on an individual question basis. If you have questions about that, about how you did on each individual question, then you can contact me and I can tell you. Or you can set up a meeting. There's going to be a folder for exam 2, just like there was for exam 1. You're going to want to print out that periodic table before you start your exam. That's the only thing that you need. There are no equations for this. So is everybody clear on the logistics? You're still using Respondus Lockdown Browser. So the same way you took exam 1 is how you're going to take exam 2. And it just covers chapters 3 and 4. Any questions about exam 2? Okay. So if we have time after going through chapter 5, then we'll circle back around and do some more examples of electron configurations. We're kind of going to hit on it again because if you watch that video for electron configurations, there's 2 types, the full and then the condensed or noble gas configuration. We're going to go over that condensed version today. So we will sort of do more examples, just not explicitly for exam review. I just skipped through everything. Okay. So this is an abridged version of chapter 5. If you have not had a chance to watch the video yet, which you had a fair amount of work to do, and you have an exam this week, so I understand. I was like, people are probably not going to watch this until after they've taken the exam. So with that in mind, this is an abridged version. You still need to get all of the details from the YouTube video. But this gives you enough background so that we can hit on the major concepts and some of the more difficult ones together as a class. We're starting with the history of how the periodic table came to be organized the way that it is today. I'm starting with Mendeleev, who is known as the father of the modern periodic table. There are a couple of other ways that the periodic table was organized prior to Mendeleev. And all of this was happening at the same time that the structure of the atom was being explored. So you've got, if you remember from chapter 4, you've got Dalton and his atomic theory. You've got J.J. Thomson. You've got Rutherford, Bohr, all these people working on the structure of the atom at the same time that we've got people trying to organize the elements in a way that makes sense and gives some trends for chemical and physical properties. We're picking up where Mendeleev said, hey, if we arrange all of the elements according to increasing atomic mass, then we see regular repeats in the properties of these elements. So his periodic table was arranged by the formula of the element's oxide. So if you combine an element with oxygen, what is the chemical formula for that? That's what he used to arrange his periodic table. I'm not going to show you what that looks like, but it is in the video. So Mendeleev did some good work, but he didn't predict everything. So he was able to predict the existence of several elements years before they were actually discovered. But what he didn't predict was the noble gases. So the noble gases are the far right column. And once they were discovered, the periodic table was expanded. These gases were originally called inert gases because it didn't seem like they did any kind of chemistry. And by and large, they don't really want to do chemistry with anything, but you can make compounds with xenon and krypton. So we call them noble gases because they don't want to mix with just any old body. The final concept that took Mendeleev's idea and created the periodic table that you see today is, instead of using atomic mass, you use nuclear charge. So we're talking about increasing atomic number. And that seemed to be an even better fit for the trends on the periodic table than atomic mass. So you will need to know the periodic law. And that just says that the properties of elements recur in a repeating pattern when they're arranged according to increasing atomic number. You combine that along with the energy levels from Niels Bohr, and you get the current periodic table. So maybe the next time you look at your periodic table, you won't just see, oh, it's the periodic table, but this was a work in progress that took years and years and years of research and observation and study to put together. So this is the summary of many people's lives put together on one sheet of paper. So that's story time for today. Now we're going to talk more about the periodic table in general. So if you don't have one, you need one. If you have a book, crack it open. If you have one printed out, whip it out. Look at the electronic one, whatever you got, because we're going to be using the periodic table quite a bit. The first two terms that I'm going to add to your vocabulary are groups and periods. The groups are the vertical columns, and all the elements within a group have similar chemical properties. The periods are the horizontal rows. There's no type of rhyme or reason in terms of the properties that the elements have in a period. The way that I remember which is which is this mnemonic. I write group going down because it's a column, and I write period going across because it's a row. Mine doesn't say that screen sharing has stopped. Does anyone else see this? Does anyone else see a black screen? Okay, if it's just one person, then it could just be your connection. Because it still says that I'm screen sharing. But sometimes Blackboard be lying to you, so. Yeah, it looks like we're still up. So that's the first two words, group and period. We good so far? There was a history lesson, which I kind of went through a little quick, but that's more, if you watch the YouTube video, I go a little slower, and I tell you exactly what things you need to know about the history of the periodic table. And then we get to the trends and things like that. So first you need terminology on how to refer to the rows in the columns. So we've got groups, we've got periods. There's all types of common names and naming different portions of the periodic table. This slide summarizes all of the ones that you will need to know. I go into detail in the lecture video that's already posted. I'll give you the highlights here. These numbers going across, those are group numbers. And you'll notice that you see kind of 1 through 18, but then you also see 1A, 2A, you see some that have a B after them. The A ones are the representative elements. It's your S and your P blocks. The B elements are transition elements. I prefer the AB system versus just the groupings 1 through 18 because the A and B give you more information about the periodic table. The one that I provide for you for exams has both. So those are the group numbers. You won't always see the different periods numbered. On this particular one they are, but you will need to know that the first row is here, second row, third row, and that equals each different period. Next, we have some common names for some of the different groups. Is there a question? Okay. I heard somebody turn on their mic, so I was like, whoa, okay. Because we're going through this. This is kind of, now we're reconnecting. So now I've lost screen share for some reason. But I'll wait until it says that we're back. But the slide that I was going over, it just tells you common names. So this isn't really conceptual stuff. It's just stuff that you're going to have to remember. So printing out that periodic table with everything labeled or labeling your own periodic table will help you remember, and you can use it as a reference. Is everyone able to see the screen? It says it's being shared, so that's strange. Let's start moseying back. You should see the screen again. Let me know if you don't. Blackboard just wanted to be a special snowflake. That's okay. So we left off talking about there's a lot of different names for the groups on the periodic table. So we're going to go over a few of them that you're going to need to know. The first group, group 1A, that's the alkali metals. They're very reactive. Group 2A, those are the alkaline earth metals. Again, my recommendation is that you recreate this periodic table and label everything. It'll help commit it to memory. Group 7A, the common name for that group is the halogens. And then, as I alluded to, group 8A, we call the noble gases. All of these green elements are transition elements. So everything that has a B after it, that's a transition element. And those that are underneath the periodic table, that's associated with filling the F block, right? Those are called the inner transition elements. They're also called the rare earth metals, but I'll be using the inner transition elements. And those can be further broken down into the lanthanides and the actinides. So no concepts here. It's just straight up memorization. So are we clear on what you're going to be expected to know? All right. So we're going to move on to periodic trends. So these trends just say, in general, when you're looking from left to right on the periodic table or up or down, this is the kind of trend you're going to see. There may be some exceptions here and there, but overall, this is what you see. And we're talking about these periodic trends are for the representative elements. I would recommend that you draw these on your periodic table. So atomic radius, that's talking about the size of the atom. As you go up a group and left to right across a period, your atomic radius decreases. Now let's rationalize this a little bit. The biggest energy level that we have is n equals 7. The smallest is n equals 1. In chapter 4, we said the bigger your energy level is, the bigger space you have for the electrons to hang out in. So if our n equals 7, let me try to make that nucleus actually in the center. If that's our n equals 7, and we have an electron hanging out there, and this is our n equals 1, it kind of makes sense that as you go up from the biggest energy level to the smallest energy level, the size of the atom is going to decrease because the energy levels are shrinking. But as you go across an energy level, you're not increasing the number of energy levels, you're just adding protons and electrons. So those protons are going to hold on to the electrons much more tightly and make your atomic radius smaller. So you're going to need to know the relative trends. And here's something that's a little bit more visual. So we're not talking about the transition elements. We're talking about the representative ones, the ones that have the A in their group name. And this just gives you a visual representation of what we just said on the last slide. The bigger you are, the further down you are on the periodic table. The smaller you are, the further to the right you are. So you'll need to be able to compare the different atoms on the periodic table. So if I asked you which one is smaller, potassium or fluorine, you'll need to know that it's fluorine because it's really far to the right on the periodic table. Does it make sense what you're going to need to know with the atomic radius trend? The next trend that we have is metallic character. And you know I don't like to do lecturing like this, but we're going to get to doing some problems in a minute. We're just going to get through the trends, and then we're going to get to some more active stuff. So metallic character, we're talking about how metallic something is. We talked about metals and nonmetals and semi-metals or metalloids. One of the ways that we can characterize something as metallic is how easily it gives up an electron from its outermost energy level. As you go from the bottom to the top of a group and left to right across a period, you're going to see that metallic character decrease. And that kind of makes sense because on the far right of the table, you have nonmetals. They're very much not metals. It's a similar trend for the atomic radius. And that makes sense too. The further away the electrons are, the easier it is to just pluck one off. The closer the electrons are to the nucleus, the harder it is to remove that electron. I didn't even check in with y'all. I'm sorry. So that was metallic character. How easily an element will give up an electron. Does that make sense? I know it's the afternoon, and this is my struggle class too. But stay with me. So in addition to these big trends like atomic radius and metallic character, we can also predict physical and chemical properties. We're first going to address the physical properties. We've talked about the trend for atomic radius, but we could also look at other physical properties like density, melting point, and atomic mass. The elements that I have here are all in group 1A. I've purposefully left all of the values for lithium blank. Let's talk about the trend that we see with the atomic radius. Well, it should follow the one that we just talked about. We're going from a bigger radius to a smaller radius. With density, for the most part in this group, we're going from a big or a high density to a low density. With the melting point, we have a small or a low melting point. And then as you go up the group, it gets higher. So we're seeing these different trends in physical properties. And of course, atomic mass, we're going from a really big one down at the bottom to a small one at the top. Given these trends, we can predict what the atomic radius will be for lithium, its density, melting point, and the atomic mass. Now, we may not be able to give exact numbers, but we can definitely say that it's going to be more or less than whatever element that comes after it. So with the atomic radius, we see the trend that the radius is getting smaller as we travel up the group. So is the atomic radius going to be bigger than 186 picometers or smaller? We're looking at the atomic radius. Yeah, I can repeat the question. We're looking at the atomic radius for group 1A elements. We don't have one for lithium. But based on the trend that we see, is the number going to be bigger than 186 picometers or smaller? It's going to be smaller. Now let's play the same game with the density. Now there is some slight irregularity where the density of sodium is actually a little bit bigger than that of potassium. But overall, we're seeing the density decrease as we go up the group. So do we expect the density of lithium to be greater or less than the density of sodium? It should be less. What about the melting point? The melting point should be higher. And finally, the atomic mass, higher or lower than sodium? Yeah, it's going to be much smaller. So that's the kind of reasoning that you're going to have to be able to do. You're also going to need to be able to do a little bit of math, and I'll show you that on this next slide. So let's say that you're given the density of calcium and strontium, and you have to predict the density of barium. If we're given information, if you want to take a stab at it, you can. I'm going to walk you through it. So we're seeing an increase in the density as we go down the group. The difference between the density of the strontium and the density of the calcium, well, we can just do subtraction. So this is the difference in density. So when we're figuring out the barium, we know that it should be bigger than strontium. So we can automatically get rid of A, B, and C. Without even doing the math, we could do that. But to figure out whether or not it's D or E, we had to figure out the difference in the density between calcium and strontium. Then you take that difference and add it to the density of strontium. So that should be your prediction, which is letter D. So not a lot of math, just got to remember which way you're going. And use the reasoning that you have of, okay, should this be bigger or smaller, to rule out answers. So how do we feel about that? It's going to vary depending on which group you're looking at. So that chart on the previous page was just for group 1A. In general, the density does decrease as you go up the group. But there can be some variations. You'll always be given the information in the problem, though. You're not going to have to guess what the trend is. So in terms of predicting physical properties, this is about as complicated as it gets. You figure out the difference between the two, and then you add something together. That's about it. We can do a similar thing for, no problem. We can do a similar thing for chemical properties. So every element in a group has similar chemical properties. Mendeleev organized the groups according to the oxide of the element. And that wasn't a bad thing to do because, by and large, when we're looking at the chemical formulas, they're going to look very similar. So again, we're looking at group 1A, and we're looking at the compounds that these alkali metals form with oxygen. They all have the same general formula of M2O, where M is your metal element. This is for group 1A. They all look the same. To put that in context of a question, let's say that the formula for the chloride of calcium is CaCl2. What is the formula for the chloride of barium? You have to know that calcium and barium are in the same group. So for this question, you would look at the periodic table and make sure that they're in the same group, the same column. If they are, then it's the same kind of formula as calcium. But instead of CaCl2, it's Ba for barium, Cl2. So does that make sense in terms of the chemical properties and how you can predict formulas based on the group? We got a no in there. Do you have a specific question? Correct. Correct. Yeah, we're not there yet. Chapter 6, we're going to be doing this, where you're going to be able to write it just based on the name. But for right now, I'll give you an example of one of the elements, and then you can write it for everything else in the group. If they were in different groups, then you couldn't do the problem. So if this were multiple choice, it would be none of the above or cannot determine, because if they're in different groups, then they don't necessarily follow the same chemical properties. Does that answer your question? Because I see the question in the chat. What would it look like if they were in different groups? The answer is you couldn't do it. Okay? So those are the trends. We're going to come back around to one more periodic trend. But before we get there, we need to cover a couple of more things. The first thing we're going to cover is the noble gas configuration. Within this, we'll be able to do some more practice of writing the full configurations too. So as practice, write the full electron configuration for manganese. And I'll circle it here for you. I'll give you a minute to get started, and then I'll start writing it out. So go ahead and write that full configuration. Even if you're not finished writing your configuration, that's okay. I'm going to just get started here. Best place to start is the beginning. We're going to start by filling the 1s with 2 electrons, because that's all it can hold. There's only the s sublevel in the first energy level, so that part's done. we need to continue on to fill in the rest of our electrons. Now we're in the second main energy level. Still in the S block, so we're going to fill the S with 2 electrons. Then we make our way across the periodic table to the P block, where we fill in all 6 of those slots in the 2P. We're still not even in the town that manganese lives in. So we move on to the third period. We're back in the S block, so we fill that with 2 electrons. We walk across the periodic table to the 3P, and we fill that with 6 electrons. Now we're in period 4. This is the town, or the period, that manganese lives in. So we're going to slow it down. We know that we can fill the 4S because we haven't hit manganese yet. But now we're in the 3D, which is in period 4. And we need to count. 1, 2, 3, 4, 5. If you add all of those numbers up, you should get 25 electrons. So that's another way that you can check your work, at least in terms of the numbers. It's not going to tell you that your order is right, but you at least have the right number of electrons. Is there a problem with the video or the audio? Okay. I'm seeing in the chat someone asked what happened. Okay. So how do we feel about writing the full electron configuration for manganese? Confident. I like that word. Okay. So hopefully, as the rest of you practice, you'll feel more and more confident. But what if I told you didn't have to write out all that stuff? Let's write the noble gas configuration together. So I abbreviate NG for the noble gas electron configuration. We're abbreviating everything else. Why not that, right? So we said that manganese is in the 4th period. So everything up to and through the 3rd period is full. The 3rd period ends here with argon. What if I just wrote argon in brackets? That would take the place of everything up through the 3p6, because that is the configuration for argon. It has completely filled the 1st, 2nd, and 3rd energy levels, excluding the D. After that, you just have to write in everything that's between argon and manganese. So everything that's in the 4th row, we need to write. That's 4s2 and 3d5. So to recap, you're going to figure out which period you're in. That's the row. Manganese is in period 4. You're going to find the noble gases, which is the far right column. You're going to look for the noble gas that is in the period above where your atom of interest is. Since we're looking at manganese in the 4th period, we need the 3rd period noble gas. And everything up through this 3rd row on the periodic table is filled. So we can write argon in parentheses, or brackets, and then fill in the rest of the way between argon and manganese. And that's where the 4s2 3d5 comes from. Does that make sense? We're going to do an example, so don't worry. If I need to explain the noble gas thing again, I can, and I can do another example. So let me just check on everybody by asking you a question. Let's say that I wanted to write the noble gas configuration for bromine. What noble gas am I going to use in my configuration? You'd use argon again. What if we were writing a configuration for fluorine? Which noble gas would you use if you were writing a configuration for fluorine? Yeah, you'd use helium, which wouldn't buy you a whole lot because that's just 1s2. But I just want to make sure you get the concept. All right. Good. So now I want you to do an example. Practice writing the full configuration. And I also want you to write the noble gas configuration for selenium. I will give you 2 minutes to get started, and then I'll jump in and help. I'm going to jump in here and start writing the full configuration. So if you're not done yet, or if you're stuck, that's fine. You always start with filling the 1s. Oh, see, bless your heart, you're writing it in the chat. I wouldn't. If you want to, you can. But it will probably take just as much time to write it in the chat as it would to write it in your notebook. So we're going for selenium here. And that is still in the 4th period. And right now, we've just filled up through the 2s, so we've still got some ways to go. I filled everything up through the 3rd row. Now I'm in the 4th row, And I'm going to fill the 4s with 2 electrons, the 3d with 10 electrons. Then I'm back to the 4 for the main energy level, and we're in the p block. So I'm filling the 4p with 1, 2, 3, 4 electrons. That is the full configuration for selenium. The noble gas configuration, well, we're still in the same exact period as manganese and bromine. And we said for both of those, we're using argon as our noble gas core. So we're still using argon. And that accounts for all of that. Now we just have to put in the difference, all of the stuff between argon and selenium. That's the 4s2, 3d10, 4p4. So how did that feel? If you were able to get through it, congratulations. The noble gas configuration really is nice, but you have to understand the full one to know what the noble gas one actually means. So in the interest of time, we're going to move forward. But if you have questions about this, don't be ashamed to ask. It's all right. Before we can talk about our final trend, we have to talk about valence electrons. Valence electrons are the ones that live in the outermost principal energy level of an atom. They are the ones that are involved in chemical reactions. The valence electrons are the s and p electrons that are beyond that noble gas core. So for this last one, for selenium, we had argon for the noble gas core, and then we had 4s2, 3d10, 4p4. The valence electrons here are the s and p electrons in the 4th energy level, because the 4th energy level is the outermost principal energy level. 4 is bigger than 3. And we're only looking at the s and the p electrons for the valence electrons. So here we have a total of 6 valence electrons. Does that concept make sense of what valence electrons are? Let's build on that. We can represent those valence electrons visually using an electron dot formula or Lewis dot structure. They're the same thing, you just may see one term or the other. The way that you draw one is you write the symbol of your element, and then you surround it with all of the valence electrons. So if we were going to do selenium, we said that it has 6 valence electrons. We're going to go around and put 1 electron on each side of the symbol. That's only 4. We said that we have 6 valence electrons. So we need to place 2 more. We're going to go back through and double up on 2 sides for a total of 6 valence electrons. If you wrote this It would be wrong. You don't want to pair up your electrons unless you absolutely have to. And the example that I like to use is if you've ever had to share your bed with a cousin or somebody when you have family in town, because ain't nobody paying for no hotel and ain't no guest rooms. You and your cousin, after they got out the car from driving for 10 or 12 hours with their funky feet, those funky feet will be next to your head. You don't want them there unless they absolutely have to be there. So if it's just one cousin, maybe they can sleep on the couch. So you're going to have them separated like this. But if it's a bunch of y'all and they're all girl cousins and you happen to be a girl, you're sharing your bed. So you pair up. Maybe that's not your life. It was mine. And you can see I may still be a little bit bitter. 12 hours in the car is a long time. If you don't wash your feet, that's not fair. I have to be uncomfortable and smell your feet. Come on, fam. We're supposed to be nice to each other. We're family. It's very rude. Anyway, chemistry. Don't pair your electrons unless you have to. That is the moral of the story. Oops. So let's try another example here. Let's say that we have nitrogen. Nitrogen has 5 valence electrons. To place those, you're going to put 1 electron on each side and then double up on one side. Doesn't really matter which side you double up on, as long as you only double up on one side. One thing that I didn't mention on the previous slide that will help you figure out the number of valence electrons. We're talking about groups 1A through 8A. So the representative elements only. Only the ones with the A. That group number tells you the number of valence electrons. So if you're in group 5A, you have 5 valence electrons. If you're in 4A, you have 4 valence electrons. So you don't have to write out the configuration and then figure it out. If you're looking at a representative element, the group number that has the A behind it will tell you how many valence electrons you have. Is that clear? So now that we've built up our understanding of the noble gas configuration and valence electrons, we can talk about the final trend for the periodic table that we're going to cover. And that's ionization energy. Ionization energy is the amount of energy required to remove an electron from that atom in the gaseous state. In general, as you go from the bottom to the top of a group and from left to right, that ionization energy is going to increase. Now, in the context of the other trends that we talked about, this makes sense. At the bottom of a group, we're talking about a really big radius, which means that your electrons are really far away. So it's going to be pretty easy to pick one off. But as that radius gets smaller, those electrons are going to be more tightly associated with the nucleus. So it's going to be harder to remove one. Likewise, as you go across the periodic table from left to right, that radius is getting even smaller because you're adding protons and electrons, but you're not increasing your energy levels. So those electrons are going to be even closer to the nucleus. So it's going to require even more energy to remove one of those electrons. So on your periodic table, you're going to want to make sure that you have all three of the trends, atomic radius and metallic character, which follow the same trend. And then ionization energy, which is the opposite. It increases as you go up a group and across a period. Is that clear for everybody? And I explain that in the YouTube video too, and I take my time a little bit more. But as long as you're like, all right, I think I know what those words mean, then we're in a good place. So this is the trend, if you're a visual person, for ionization energy. That brings us to the final kind of big topic for today, which is ionic charges. If you don't understand ionic charges between this live lecture and the video on YouTube, you will need to make sure that you understand it before chapter 6. You need to understand ionic charges before we can talk about the language of chemistry and how we can write chemical formulas based on the names. So don't blow this part off. Chemistry is cumulative. We're going to start with the easier ions, which are the positive ions. Most of the periodic table, it's metal. And metals react by losing their valence electrons, which we were just talking about those. The valence electrons are the ones in the outermost energy level. Those are the ones that participate in chemistry. And metals participate by giving those valence electrons away. That means that they form positive ions. So if we look at sodium, which is a metal, this is the full electron configuration. 1s2, 2s2, 2p6, 3s1. Of these, the 1s2, 2s2, 2p6, 3s1, which one represents the valence electrons? Where are the valence electrons for sodium? Remember, the valence electrons are the outermost energy level. So it's going to be in the one that's got the biggest main energy level. That's going to be the 3s. So the outermost energy level is the one that has the highest N. So these are your valence electrons. When sodium participates in chemistry, it's going to lose those valence electrons. So just the neutral atom, it's got 11 electrons, and it's also got 11 protons, because remember, neutral atom, the number of electrons is equal to the number of protons. If we lose this one valence electron, We now only have 10 electrons, but we still have 11 protons. They're not equal. You have more protons than you do electrons. So you have a positively charged ion. Hence, there's the plus sign. So that is the sodium ion. Notice how that electron in the 3s is gone. So let me know if you're still with me. We got rid of the valence electron for sodium to form a positive ion. Does that make sense? Good. In general, we got to know. Okay, do we have a specific question, or you just need me to walk through it again? Okay, yeah, I can go over that. Yes. Yes. So remember the number of protons you get from the atomic number on the periodic table. So the periodic table, you look at it, sodium has an atomic number of 11. That means you have 11 protons. If you add up all of these little numbers here, you get 11 electrons. So even if you don't go with the approach of, well, they should be equal because this is a neutral atom, the electron configuration tells you that there are 11 electrons. When we go over to the sodium ion, we no longer have that 3s electron. It's gone. So when you total up what you have, you only have 10 electrons. We did nothing to the protons. The protons remain the same. So you still have 11 protons. You just have one less electron. And that means that you're now a positively charged ion. Does that make more sense? Okay. I see another question in the chat. What makes it negative in the first place? So, are you referring to the electrons? That's just the property of electrons. Electrons are negatively charged. Protons are positively charged. Then can you be a little bit more specific with your question? No, the sodium was neutral before. We had the same number of electrons as we did protons, so that means that the charge on it was 0. Then we lost 1 electron. So there's an imbalance. We only have 10 electrons now, but we still have the same number of protons because our chemistry is not doing anything to the nucleus. We're just swapping electrons. That's all chemistry is. I feel like there was a big light bulb over your head right then and there. And that's good. Good. Okay. In general, when we're talking about metal representative elements, the group number is going to equal your ionic charge. So it can do two things for you. Let's say that we are in group 2A. The A tells us we're representative. Group 2, those are the alkaline earth metals. So you really need to know your metals on the periodic table. Which ones are metals and which ones are non-metals or semi-metals. If you're in group 2A, just by the fact that you're in 2A, I know two things. You have 2 valence electrons, and that your ionic charge is +2. Because when you react with something, you're going to lose those 2 valence electrons. So you're going to be +2. Let's check your understanding. If I'm a group 3A metal, how many valence electrons do I have? Yeah, we're not talking about the transition metals. Transition metals can have multiple ionic charge states. So we ain't talking about those. So we know just from the group number that there are 3 valence electrons. What's my ionic charge if I'm in group 3A metal? It's going to be +3 or 3+. Doesn't really matter which way you write it. So for metals, simple as that. Now let's do an example. We talked about the charge. We've talked about electron configurations. Let's put those two concepts together. Let's look at a magnesium ion. I'll label these for you. What is the charge of a magnesium ion? It should be 2+, because it is in group 2A. Boom, done. That's the charge. But now we need to talk about the electron configuration. To do that, I'm going to first write the configuration for the neutral atom. We'd fill the 1s, the 2s, the 2p, and then we'd fill the 3s, and then we're done. We said that the outermost electrons are the valence electrons. So when magnesium forms an ion, it's going to lose those. So our configuration for the ion, and I'm putting ion in parentheses just to stress that it is not the neutral atom anymore. It is a magnesium ion. That is the configuration for the magnesium ion. And that was the full configuration. Let's write the abbreviated forms for both of these. So if we're starting with the neutral atom, what noble gas am I going to use for my noble gas core for the abbreviated version? I'm going to use neon. Then I have to add on everything between neon and magnesium. So I have to add on the 3s2. Again, these are my valence electrons. So when I lose them, what do you think my noble gas configuration is going to be for my ion? It's just going to be the neon in brackets because we lost those valence electrons. So in terms of electrons, the magnesium ion looks like neon. So let me know if you follow or if I need to go through that again. I have another example to do. Okay. So that was the positive ions. Now we're going to talk about negative ions. It's a little bit trickier. Nonmetals gain electrons to form negative ions. When we're talking about nonmetals, we're talking about groups 5A through 7A. Let's use oxygen as an example. Look at your periodic table. What is the atomic number for oxygen? So that means oxygen has 8 protons. In a neutral atom, which this is so far, we're also going to have 8 electrons. And if you total up these numbers in the configuration, you get 8. Oxygen wants more electrons. It's so close to having that noble gas configuration. So it is going to gain electrons to fill the 2p. Now, we still have 8 protons. We haven't done anything to the protons. But we've gained 2 electrons. So that now we've got more electrons than protons. So we're forming a negative ion. Does that make sense so far? You don't have to know where the 2 comes from, but understand that we gain 2 more electrons. So now our charge is -2. It's the same thing for every other non-metal. In general, for non-metals, and again, we're talking group 5A through 7A, you can determine the charge based on the group number. You have to take that group number and subtract 8. Look at your periodic table and tell me what group oxygen is in. Oxygen is in group 6A. Yes. So to figure out the charge without writing out the electron configurations, we can say that our charge is going to be equal to the group number, which, remember, it has to have an A after it. That number is 6. You subtract 8, and that gives you -2. So all the elements that are non-metals in group 6A have a -2 charge. How we feel about that so far? Now we're going to do the same thing that we did with the positive ions, only with the negative. We have to be able to write the charge and electron configuration for negative ions. We're going to use sulfur as our example. It's in the same group as oxygen. So for the charge, we already know that it's going to be -2. Check. Let's do the electron configurations and take a look at how that changes when you go from the neutral atom to the ion. With the full configuration, you start with the 1s, then you fill the 2s, the 2p, then the 3s, and now we're in the neighborhood of sulfur, so we'll slow down. We've got 3p, 1, 2, 3, 4. So this is the neutral atom. We gain electrons if we're negative. And since our charge is -2, that means we have to gain 2 electrons. So for our ion, we need to add 2 electrons wherever they'll fit. Can't fit it in the 1s, that's full. The 2s is already full. 2p, full up. 3s, sorry. It's going to be 3p6. That's exactly right. So we just completed the P for the third energy level by gaining 2 electrons. Now let's use our noble gas configuration. The neutral atom is going to have neon for its core, and then the 3s and 3p electrons. When we add 2 electrons, does anyone have a guess as to what noble gas it's going to look like after we add 2 electrons, because we're completing the 3p, what should it look like? It looks like argon. So with the negative ions, you're gaining electrons. So you're skipping ahead to what the noble gas looks like in that row or period. So if I told you that you had a selenium ion and that it was negatively charged, what noble gas would the ion look like? It would look like krypton. Doing these charges is going to take practice. And if you didn't get a chance to watch the video before today, it might be like, ooh, okay, Dr. Hefner, I'm going to need a break and a drink right now. I'm thirsty because my brain is working too hard. And I get it. But don't give up or leave it at that. Make sure that you practice and you come see me in office hours if you have questions. The last concept builds on that whole idea of ionic charges. You can look at atoms and ions with the same electron configuration. They are isoelectronic. So just like how we said that the sulfur ion looks like argon, they both have 18 electrons. That's an isoelectronic series. So we just made one inadvertently just by going through and writing those configurations. That was on purpose on my part. So you have to understand the positive and negative ion charges and how to write the configurations for those ions before you can get the isoelectronic series. So we're not going to do any examples per se about this, but it is a concept that you will need to know. I ended that too soon. We're going to keep those annotations. So I forgot to put in a reminder slide, which is kind of ironic, I know. But the things that you're going to need to know. There's no check-in this week. You have an exam that is available Wednesday through Friday on chapters 3 and 4. You should prioritize that. There's the exam 2 review. The exam 2 review answer key should be available now in Blackboard. So do those. Ask any questions that you may have in office hours, which are officially Wednesdays from 2 to 4. If that does not work with your schedule, you can always send me your question through course messages, or you can set up a time through course messages and we can meet individually. Virtually, of course. Make sure that you do well on that second exam. It's all multiple choice. You don't have to upload your work because there's really no math. Then make sure you do your Chapter 5 Mastering Chemistry homework and quiz. I don't want to pile anything else on top of that. Next week, we're going to hit Chapter 6. And the week after that, you have another exam on chapters 5 and 6. So this is going fast. If you have any questions for me about material that we covered or about the exam, you can let me know. If you're good, you're free to go. Otherwise, stay and ask your questions.